For the X-ray photoelectron spectroscopy, or XPS spectrum, we analyzed residue that formed during an engine test. The analysis indicated that the residue contained copper from overheating cooling components and carbon from incomplete combustion. To generate the combined XPS spectrum, we first identified the characteristic core level peaks for each element present in the sample. For carbon, we included the C1s peak at around 285 electron volts, which is typical for hydrocarbon or graphitic carbon produced during incomplete combustion. Because the sample is measured in air, we also expect some surface oxidation. For that reason, we included an oxygen 1s peak at around 532 electron volts to represent oxygen from atmospheric exposure or oxidized surface species. Next, we added the characteristic copper peaks. Copper has two major XPS peaks in this region. The copper 2p 3.5 peak at about 933 electron volts, and the copper 2p 1.5 peak at about 953 electron volts. Since the copper components were overheated and exposed to air, we also considered the possibility of oxidized copper, which can produce satellite peaks at slightly better, higher binding energies. Finally, we combine these individual elemental signals into one spectrum by plotting intensity versus binding energy and placing each peak at its characteristic binding energy. This produces a combined spectrum that clearly shows combustion from copper, carbon, and oxygen, which is consistent with residue formed from engine components and incomplete combustion products.
Hi, my name is Priscilla, and I'm responsible for the IR and mass spectrometry analysis for our rocket fuel study. I generated these spectra using AI prompts calibrated with NIST chemistry webbook data to ensure the P compositions and intensities are scientifically accurate. So for the IR analysis of the methane combustion, our reactant sketch shows only methane peaks, specifically the CH stretch at 3019. Oxygen is absent because it's IR inactive. In the product sketch, the methane is gone, replaced by CO2 at 2349, and broad water vapor bands. Because of the 1 to 2 stoichiometry of the reaction, the water bands are noticeably more intense, confirming successful and complete combustion. For question 3, we compared two fuels. The methane spectrum is simple and clean, defined by a molecular ion peak at M over Z16. In contrast, the kerosene fuel used in rockets like the Falcon 9 is a complex mixture of C10 and C16 hydrocarbons. Its spectrum shows a comb-like pattern with repeating clusters every 14 mass units. The most critical markers here are the fragments at M over Z 43 and 57, which act as the chemical fingerprints for this high-performance fuel. Together, these techniques allow us to monitor fuel purity and combustion efficiency in real time. I'll now pass it over to discuss our XPS findings.
Hi, my name is Caitlin, and I'm going to talk about section 4 and 5. We'll look at the instrumentation behind the three analytical techniques we use to analyze these rocket fuels and their combustion: IR, XPS, and mass spectrometry. So first, for the infrared spectroscopy, we use an IR spectrometer to identify molecules like methane and combustion products by measuring their light absorption. The process starts at the radiation source, which sends infrared light through the sample compartment. An interferometer processes the light so the detector can distinguish frequencies and produce a spectrum, allowing us to see the specific molecular vibrations of our reactants and products. As for the XPS, which is essential for analyzing surface residues like copper and carbon found on engine stands, this instrument uses an X-ray source to eject core-level electrons from the sample. Because electrons are easily blocked by air, this must happen in an ultra-high vacuum chamber. An electron analyzer then measures the kinetic energy of these electrons, which the detector uses to identify exactly which elements are present on the surface. Finally, for mass spectrometry, we identify fuel combustion by weight. An ion source hits the fuel molecules with electrons to create ions, which a mass analyzer then separates based on their mass to charge ratio. The detector records these fragments, giving us a unique fingerprint for each fuel type. Then I gave another brief explanation here and another image here of an example of an instrument. And for part 5 of the discussion, we compared methane-based and kerosene-based fuels. Methane is a highly effective and burns very cleanly, making it ideal for reusable engines like Starship, though it requires complex cryogenic storage. On the other hand, kerosene is much denser and easier to handle at room temperature, but it produces heavy soot and coking, which can leave the carbon residue we analyzed earlier via XPS. So in conclusion, the differences reflect in our analysis. Methane shows simple, predictable patterns in IR and mass spec, while kerosene products much more complex fragmentation and surface contamination.